You know, triangles, they seem so simple, right? One of the very first shapes we all learn. But what if I told you that hiding inside every single one of them is this special line, a line that has two kind of like predictable superpowers? Well, today we're going to unlock those secrets.
So here's what we've got on tap. First, we're going to figure out what this hidden line even is. Then, we'll dive into the theorem that gives it all its power. After that, we'll actually prove it works, to be sure. We'll see it in action with a couple of examples, and then wrap things up by looking at why any of this really matters in the first place.
Okay, let's jump right in. First up, the basics. What exactly is this hidden line we're hunting for inside a triangle?
You know, the secret isn't some lost treasure map or anything. It's actually a rule. Triangles might look simple on the surface, but they're built on this really elegant foundation of powerful geometric rules, and we're about to uncover one of the absolute most useful ones.
And the hero of our story today is something called the midsegment. The name itself gives you a massive clue, right? Mid for midpoint, segment for a line segment. It's literally just a line that connects the midpoints of any two sides of a triangle. Super simple.
All right, take a look at this triangle ABC. You see those points? M, N, and P? Well, M is the exact middle of side AB, P is the middle of side BC, and N is the middle of side AC. So when you connect those dots, the lines you get, MP, MN, and NP, those are the triangle's three midsegments. And yep, that means every single triangle has exactly three of them.
Okay, so now that we know what a midsegment is, it's time to talk about what makes it so special. It has these two, let's call them superpowers. And officially, these powers are all wrapped up in what's known as the triangle midsegment theorem.
And this theorem, this is what makes the midsegment such a game changer. It's a guarantee. It tells us that two specific things will be true about this line every single time. No exceptions. And these two facts are the real key to unlocking its power.
So what are these two superpowers? Here they are. First, one's about direction. The midsegment is always parallel to the third side of the triangle, the one it isn't touching. And second, it's about size. The midsegment is always exactly half the length of that same third side. That's it. Parallel and half the length. Those are the two big takeaways.
And this is just how you'd see those two ideas written down formally, in a textbook. Theorem 6.8. It just says that if you have a midsegment, like DE here, then it has to be parallel to that third side, AC. And its length has to be exactly 1/2 the length of AC. It's just putting our two superpowers into official math language.
Okay, but wait a second. How can we be so sure this works for every single triangle out there and not just the couple we've looked at? Well, in math, we don't just take things on faith, right? We prove them. So let's walk through a really quick proof on a coordinate plane just to see for ourselves why this theorem is always, always true.
Our strategy here is actually pretty simple. First, we'll just plop a generic triangle down on a coordinate plane. Then, we'll find the coordinates for the midpoints. And from there, it's just a matter of checking our two superpowers, right? We'll compare the slopes of the lines to make sure they're parallel, and then we'll compare their lengths to make sure one is exactly half the other. Easy enough.
So, for our proof, we're going to use this specific triangle, triangle OBC. Our whole goal here is to show that that little midsegment, DE, is parallel to the bottom side, OC. And, you guessed it, that it's exactly half its length. All right, first up, let's check if they're parallel. So we use the midpoint formula to get the coordinates for points D and E. And when you calculate the slope of that midsegment, DE, you get 0. And what's the slope of the base, OC? Also 0. Since their slopes are exactly the same, the lines are, without a doubt, parallel. So superpower number 1? Check.
Okay, now for the second part, the length. We use the distance formula, and what do we find? The length of our midsegment DE turns out to be just P, and the length of the base OC, it's 2P. And there you have it. P is exactly half of 2P. It's that simple. Superpower number 2 is confirmed, and our proof is officially done.
So, we've defined it, we've proved it, now for the really fun part. Let's put this theorem to work and see how it helps us solve some actual problems.
This first problem should look pretty familiar. It's a lot like the proof we just did. We've got this triangle, JKL, sitting on a coordinate plane, and our job is to prove that the midsegment, MN, is parallel to the side JL and that it's also half its length.
And when you run the numbers, yep, they check out perfectly. The slope for MN is -1/4.
The slope for JL, also -1/4. So boom, they're parallel. And what about the lengths? Well, the length of MN is the square root of 17, and the length of JL is 2 times the square root of 17. So it is exactly half. The theorem holds up.
But hey, this theorem isn't just for solving problems on a graph. It shows up in the real world, in visual ways too. I mean, take a kaleidoscope, for example. Those beautiful, complex patterns are really just made up of tons and tons of repeating triangles. Let's zoom in and take a closer look at one.
So, looking at this pattern, let's say we know two things. That point E is the midpoint of side AB, and point D is the midpoint of side AC. That's it. That's all we need to know. We don't need any numbers, no coordinates, nothing. The midsegment theorem just lets us say with 100% certainty that the line DE has to be parallel to the line CB. It's an incredible logical shortcut.
So when you boil it all down, what's the big deal? Why does this little hidden line inside a triangle actually matter?
Well, it really comes down to this, that one simple line connecting two midpoints instantly gives us two incredibly powerful pieces of information. We know for a fact that it's parallel to the third side, and we know for a fact it's exactly half that side's length. And that makes it a fantastic tool for figuring things out. Think about it. You could find the distance across a lake without ever having to cross it, or prove that the support beams in a bridge are perfectly aligned.
So I'm going to leave you with a challenge. This simple, elegant rule, it's literally built into the world all around us. So now that you're in on the secret, where are you going to see it next? Maybe in the trusses of a bridge, the rafters holding up a roof, or even in the pattern of a quilt. Keep your eyes open because I promise you're going to start seeing it everywhere.